Thermodynamics, a quick recap of the lesson. Thermodynamics, as the name suggests, this is a study of physics which deals with heat flow. Thermodynamics, heat flow, the flow of heat. Okay, that's the principle of this lesson. So the next is, first thing that I taught you in thermodynamics is the what is meant by thermal equilibrium. A thermal equilibrium is when the temperature is a constant. Take two systems A and B. If the temperatures are the same, then you can say that the two systems are in thermal equilibrium with each other. The first thing. The second thing that I taught you is the zeroth law of thermodynamics. Zeroth law of thermodynamics. Okay, what is zeroth law of thermodynamics? Is supposing you have a system A and system B which is separated by an adiabatic wall. An adiabatic wall is like a flask wall which is non-conducting, insulating, whatever you call it. It's called adiabatic. There is a system C between which there is a diathermal wall. Diathermal means conducting wall. Adiabatic wall means non-conducting. Adiabatic wall. So then you know the temperature of this is TA, this is TB, and this is TC. And since there is no transfer of heat from TA to TB, but there is still exchange of heat from TA to TC and TB to TC, because it has got diathermal wall which allows the flow of heat. Therefore, TA is equal to TC, TB is equal to TC, and therefore TA is equal to TB. And this is known as zeroth law of thermodynamics. That is, when you have three systems A, B and C, where A and B are separated by adiabatic wall, bracket, no flow of heat is allowed, and there's a body C, system C, which is separated from A and B by a diathermal wall which allows exchange of heat. So then TA is equal to TC, TB is equal to TC, therefore TA and TB will be equal. This law is known as zeroth law. Okay. The next thing that I taught you is about a pressure and volume. So you have take a container. Okay, you know that fill a gas in it. Just fill a gas and attach a piston to it. Okay, so this contains a gas and there's a piston. Here we are talking about the whole lesson. We will be talking about an ideal gas scenario. The main first of all, before proceeding, you should know general physics about ideal gas. Ideal gas is one in which the collision of the molecules collide. The collision of the molecules is perfectly elastic. It's all elastic collision. When you call it elastic collision, which means there is no loss of energy. Why? Because there is no force of attraction or repulsion. It's not possible, right? But in ideal gas it's possible. No force of attraction or repulsion. And therefore there is no potential energy. These are the points. So in an ideal gas, the collisions are perfectly, it's elastic collisions and no loss of energy. Elastic collision itself means no loss of energy. And no loss of energy means there is no force of attraction or repulsion, and so no potential energy. But there is an energy. Generally, the energy of a gas can be classified in two kinds. One is potential energy, another is kinetic energy. That's called internal energy of any system. Can be classified into potential energy and kinetic energy. However, I just saw that in an ideal gas, there is no potential energy. There is no potential energy due to these reasons. Okay? And so then there is only kinetic energy. So in the entire lesson, when we talk about internal energy, it refers to only kinetic energy. Therefore, internal energy of any system in this lesson, when it comes to ideal gases, refers to only kinetic energy. And you know that the kinetic energy increases when the temperature increases and the kinetic energy decreases when the temperature decreases, and vice versa. something you got to understand. This is something you need to know. This is something that you got to know. Okay, so now coming back to this, I'm going to talk to you about, again, this is general physics that you're supposed to know. General physics. Okay, the next thing that you're supposed to know is, okay, it's the first law of thermodynamics, before which I'll talk to you about indicator diagram. An indicator diagram is one where it's a PV graph. If you're going to plot a graph, as pressure increases, volume decreases. As pressure decreases, as pressure increases, pressure will increase and volume will decrease. So something that you know. So this is the graph that you should draw at constant temperature. At constant temperature, that's a keyword. You have to keep one parameter as constant. So pressure and volume, pressure is decreasing in this direction, which means compression is happening. Volume is volume is increasing in this direction. Volume is increasing means expansion is happening. Pressure is decreasing and expansion is happening. In this case, if you see, pressure is increasing and volume is decreasing. So it's compression. The same diagram, you understand which direction is compression. And in a PV graph, this is called an indicator diagram, a PV graph. And if it was a straight line, you can find the area under the graph, which is P into V, which is L into B kind of thing, which is nothing but work done. The work done is force into displacement, and force itself is pressure into area into displacement, and area into displacement is volume. So PV is nothing but the work done. It's easy to find the work done if it's a straight line, but unfortunately, that's not how it is. It's a curve. And how to find the work done under a curve? That's when integration comes into play. Just take a small rectangle of dV. This whole graph is from V1 to V2. The area of this rectangle is y coordinate P into dV. P into dV is the area of this Kuti rectangle, which can be integrated from V1 to V2, and that will be the formula for work done. So thus, from the indicator diagram, you understand how is the graph for expansion, compression at constant temperature, and how do you write the work done by calculating the area under the graph, which is basically by integration. So that's what it is. So now comes the first law of thermodynamics. First law of thermodynamics. What is first law? Is take the piston inside which this gas, and imagine heat. Don't say heat is supplied, instead say heat is absorbed. Heat is absorbed by the system. The heat absorbed, heat is always referred to as delta Q. Delta Q is a change in the heat. Q means heat, but delta Q is a change in the heat. Okay, so delta Q is the change in the heat, or the heat absorbed by the system, which will go about in increasing the internal energy of the system. Delta U refers to internal energy of the system, and also doing the piston, the gas doing work on the piston will get pushed up, which means this is delta X through which it's risen, this height, and this area of cross section is A, and so this volume is a change in volume, which is A into delta X, which is nothing but a volume change. Delta V, we can say delta V is the volume change. And you guys know the work done is P into delta V. So that's the work done. This is how we get work done is P into delta V. Okay, so then delta V itself is A into delta X. So you understood this. And the heat supplied, the delta Q which is supplied, goes about in increasing the internal energy of the system, and also the system doing work on the surrounding. That is the gas pushing up the piston. The system doing work on the surrounding is P into delta V. So this law is known as first law of thermodynamics. This could have been, this they will say plus or minus Q when they write, where plus delta Q stands for heat absorbed and minus delta Q stands for heat released, the sign convention. I told you an example. When ice is becoming water, heat is absorbed. But when water is becoming ice, heat is released. So in that case, minus delta Q. We also did a numerical based on this. Very, very important formula. We did 2 numerical based on this. Let me do that, and let me do a recap of those 2 numericals now. Okay, one second, hold on. But before doing the numericals, you should know certain things which are basic physics, okay? Such as what is specific heat, what is latent heat, okay? So I'll just tell you those, okay? Without which you cannot proceed with this lesson. So to understand a specific heat, say I told you your mom is boiling water. She boils water because you have fever. You're asking you to you want a mild hot water. So she is boiling it from 32-degree room temperature to some 50 degrees Celsius. So when she places a thermometer, you notice a change in the temperature. Delta T is there. But there is no change of state. Because until 100 degrees Celsius, it will remain to be water only. There is no change of state. But there is delta T. There is delta T, yes. When there's a change in the temperature and there's no change of state, this is one condition, okay? The heat supplied is always proportional to the mass of the substance into the change in temperature that you require. That much heat you should supply. A big 2 liters of water means more heat. 5 liters of water, more heat. Similarly, your mother wants 50 degree or 60 degree depending on it. So M into delta T. So delta Q is equal to C into M into delta T, where C is a constant known as specific heat. Specific heat. Therefore, the C is equal to delta Q by M into delta T. Delta Q is nothing but the heat supplied. Sometimes the SI unit for specific heat, therefore joule per kg per Kelvin, or sometimes M can also be called as moles, number of moles, N, delta Q by N into delta T. So it's generally joule per mole per Kelvin, joule per mole per Kelvin, or can even be degrees Celsius sometimes, okay, depending on question. So this is specific heat. The word specific heat comes in this case where there is a change in temperature in the thermometer, but there's no change of state. When will the change of state happen? When the water starts evaporating into vapors. That happens at exactly 100 degrees Celsius. Until all the water evaporates, the small drop, it will still show only 100. The thermometer will always show only 100 degrees. Therefore, there is no delta T. But there is change of state. Yes, change of state is there. So then therefore the delta Q that is supplied is not contributing to any change in temperature, right? It's only contributing to the heating of the mass. Just mass is delta Q therefore is equal to L into M, where L is known as hidden heat or latent heat. Hidden heat or latent heat. Thus L is equal to delta Q by M. So latent heat is that, it's just joule per mole or joule per mole or joule per kg or something like that, okay. So then that's about latent heat. Latent heat is hidden heat. Why is it hidden? Because when you want to change it into vapor, obviously you have to break away the molecular force for it to become vapor. There will be force of attraction. This is water. This is not gas, ideal gas for me to say there's no force of attraction. It's water. There will be force of attraction. It has to break away from the molecular forces, and so then the heat supplied goes away in breaking the molecule, breaking the molecular force or setting free the molecules. So that is why it's called hidden heat, because it's not visible. Where does that heat go is not visible. It's something that we have to predict. So this is something you need to understand to be able to do the numericals. I did 2 numericals today, wherein I did one sum where it consisted of 1 gram of water, which at 100 degrees Celsius is obviously is going to get converted into steam. You know that. And that steam, the volume of that steam is given to be 1671 centimeter cube. You can look at Aurora. It's there in page number 12.7 in my Aurora. If you don't have Aurora, you must buy Aurora. A second volume at least. 1 gram of water at 100 degrees Celsius converted to steam of 1671 centimeter cube. Find the change in the internal energy of system, where the latent heat of the system is given to be 2256 joule per gram. You're going to convert everything into SI unit, okay? 1 atmospheric pressure is 1.013 into 10 to the power 5 Newton per meter square. Okay, these are all given. You know, if you want to find the internal energy, delta Q is equal to delta U plus P into delta V. So delta U, which is the internal energy, is delta Q minus P into delta V. How to find delta V, P into delta V? Okay, first of all, in this question, it's been given 1 gram. I need to find what is the volume so that I can find delta V, which attributes to change in the volume. Because I know the gas odor volume, but I don't know the water's volume. A 1 gram will have how much volume? Mass is given. You know, density is equal to mass by volume. Mass, you want volume is equal to mass by density. Mass is 1 gram, converting into kg, 10 to the power minus 3 kg. By density of water is 10 to the power 3, therefore it's 10 to the power minus 6 in SI unit, kg per meter cube density. So volume is equal to 10 to the power minus 6. So meter cube. So that is the volume, which means it's, this is 1671 centimeter cube, which is the steam here, which is 1671 centimeter to meter is 10 to the power minus 2, whole cube is 10 to the power minus 6. Therefore, change in the volume delta V will be 1671 into 10 to the power minus 6 minus 1 into 10 to the power minus 6. This is this one minus this one. That is the volume of steam minus volume of the water, which will be 1670 into 10 to the power minus 6. Now I know delta V, I can substitute it here. I know pressure, which has been given 1.013 into 10 to the power 5, given in the question. Even otherwise I should know. 1670 into 10 to the power minus 6. I got P into delta V, substituted. What is delta Q? Delta Q here, it is latent heat or specific heat? No, it is latent heat because it's 100 degree and it's boiling, it's converting to vapor, which means hidden heat. So L into M. What is L? L is given to be 2256 joule per gram. I want to convert into joule per kg. So 2256 by kg means 10 to the power minus 3 kg. So it will become 2256 into 10 to the power 3 into mass is 1 gram. 1 gram of water is 10 to the power minus 3 kg of water. So this and this get cancelled. Minus, you just have to multiply these two. This will become 10 to the power minus 1. So 1670 into 1.013 into 10 to the power minus 1. This has to be multiplied separately. This is 2256 and then you have to subtract it to get the answer. Okay, the answer turns out to be 2086 joules. You can probably check out this. We can approximate this too. See, if I'm going to approximate this, let's keep this as 2256. Okay, let's keep this as, no, you just have to calculate this, multiply this too, and then it is actually minus 162256, no? 2256 minus 167, because 10 to the power minus 1 is there, into 1, if I'm going to ignore that 1.013. So 2256 into 1 divided subtract by 167. This will be 7 means this 16. So this 9. This will be 4, 14, 8, some 89. And there is a 2089. joules. Yeah, I got it. So I'm approximating this in the exam. You just do it, but this will not be asked, but this will help you to understand the real purpose of learning the first law. So that's what it is. Let's go to next sum where it involved freezing. It involved freezing. Yeah, the water is freezing. Question number 7, example 7 in the book. At 0 degrees Celsius, at normal pressure, which is 1.013 10 to the power 5, the volume of 1 gram of water again increases from 1 centimeter cube to 1.091 centimeter cube. You all know one good example that I told you. In a freezer, take a bottle, glass bottle, fill it with water, put it in the freezer. It'll break because the volume increases. When it freezes, the volume increases. So that's why water bottle is breaking. So it is. Can you see? So 1 centimeter cube to 1.009. So we can find change in volume readily. But the thing is, they've given 1 gram. Okay, but we know change in volume. There's no need to break our head here. So the change in volume itself is 1 minus 1.091 minus. So it will be 0.091 centimeter cube. You want to convert to meter cube, 0.091 into 10 to the power minus 10 to the power centimeter to meter minus 2, so 10 to the power minus 6. That will be your delta V. So you found delta V, you have to multiply with P. So work done is P into delta V, which is 1.013 in 10 to the power 5 into 0.091 into 10 to the power minus 6. That will give you work done. In this first law, delta Q is equal to delta U plus P into delta V. Here the water is freezing, so it's minus delta Q because heat is getting released, not heat is absorbed. So therefore delta U is equal to minus delta Q minus P into delta V. How to find delta Q? Delta Q, here again it is latent heat, so it's L into M with a minus sign, minus P into delta V is equal to delta U. Minus L, latent heat has been given in the question. It's been given as 80 calorie per gram. Latent heat. Okay. Latent heat of fusion, that's called latent heat of fusion. And the previous one was latent heat of vaporization. Okay, in the evaporation. So the calorie, you know how to convert 1 calorie is 4.2 joules. So 80 into 4.2 joule, converted into joule per gram, converted into kg is 10 to the power minus 3. So you can multiply this, 8 2s are 16, it was 32, 33 into 10 to the power 3, and that will be your latent heat in joule per kg. So then is 336 into 10 to the power 3 into mass is 1 gram, which is 10 to the power minus 3 kg. Minus P into delta V is something you can substitute from here as 1.013. We can take it as 1 also, okay, for convenience. And 0.09 into the power will become 10 to the power minus 1. So it's going to become minus 336 minus 0.009. So minus 336 minus 0.009 will be minus 336.009. You're just going to add both of this and you get an answer which will be delta Q, which will be delta Q is in joules. But having said that, this answer in the book is in terms of calories, and so to convert joule to calorie, you just have to divide it by 4.2. Divided by 4.2. Would we get the answer? So let's take it as 336 by 4 to approximate. 8 4s are 32. 4 4s are 64 calories. So something approximate you get. So this is the way you have to do the sum. I hope you understood the way in which you got to do the sum. That's what is important. It's not about anything else. So understood this is application of the first law. This is the application of the first law. So next is I taught you what is Mayer's formula. What is Mayer's formula? The Mayer's formula is Cp minus Cv is equal to R, and how to derive the Mayer's formula. The basics of it is first law, where delta Q is equal to delta U plus P into delta V. This is specified at constant pressure. You know it's C's formula is delta Q by M into delta T or N into delta T, taking it as 1 mole. So it's delta Q by delta T, so dividing by delta T on both sides. Delta U by delta T plus P into delta V by delta T. Thus you got your first equation. This is the specific. You can remove this, so you got Cp. Now let's do Cv, which is specified at constant volume. Again the same formula. So then therefore you can divide both sides by delta T, delta Q by delta T as usual. You can divide both sides by delta Q by delta T. So delta Q by delta T in this becomes delta U by delta T. But you cannot do this because constant volume means delta V is equal to 0. Therefore this whole thing becomes 0. So this itself is not there. So let's remove this. So thus you get the second equation for Cp and Cv. Did you notice this is nothing but Cv? So Cp is equal to Cv plus P into delta V by delta T, substituting in one equation number 1. So Cp minus Cv is equal to P into delta V by delta T. You know Pv is equal to nRT. Considering you can't consider both constant pressure and constant volume. One of the cases you should take. So we are taking constant pressure and differentiating delta V by delta T will be equal to let's consider 1 mole, and so R into delta T by delta T, which is getting cancelled. So instead of this whole thing you can substitute R. So Cp minus Cv is equal to R. If they give you specific heat at constant volume, you can find, you know, R is nothing but 8.31 joule per mole per Kelvin. In the school they are writing 1.98 calorie per mole per Kelvin also, because by dividing it by joule to Kelvin by 4.2. So you can keep any of those, and so with that you can conveniently, I would prefer joule per mole per Kelvin, not calories, because that's my convenient for me. That's all. Depending on whatever is your answer, you can write calorie per mole per. So thus you can find mole per Kelvin Okay, that's all. So this is one Mayer's formula which will be useful. If you know Cp or Cv, you can find one of those, you know, you can find the other one. The best part is that. And then what did I teach you is isothermal process. I taught you what is an isothermal process. Isothermal process is like iso, temperature has to remain the same. So if your mother is giving me a normal bottle, okay, which has got water at 50 degrees Celsius, I have to maintain it at 50 degrees Celsius but without a flask, which means I have to constantly supply heat, because over a period of time it will become 32. So panite irundadana it will maintain at 50. So then the absorption of heat or release of heat can also be allowed. Exchange of heat is allowed. In an isothermal process, exchange of heat should be allowed. Why? To maintain, iso means to maintain constant temperature. And for this you need conducting walls, because exchange of heat should be allowed. Number 3, the process of expansion or compression of the piston must happen slowly, slow process, so that it's enough time for processing and exchanging. This is what is isothermal process. So the key points on isothermal process is this. And again, your whatever expansion or you're doing or compression you're doing, you have to do it slowly. That much you understood. So in the isothermal process, let's find gas equation. You know PV is equal to nRT, where T is constant. Therefore PV itself is a constant. That is the gas equation. That's your first thing in isothermal process. Second thing is, let's derive work done in isothermal process. The work done in isothermal process. You know, work done according to us is integration of P into delta V. Yeah, P delta V, V1 to V2, we already know that. This is the work done from the graph. Yeah, from the PV graph, we know that's the work done. Everybody knows this. And so then, but you know, here PV is equal to nRT. But considering n is equal to 1 here, PV is equal to RT. Or keep it like that, PV is equal to nRT, let it be. So what is P from here? nRT by V. Just substitute it here. nRT is a constant, so take it out. 1 by V into dV alone has to be. Delta V and dV are same, you can put whatever you want from V1 to V2. What you must remember is differentiation of log x is 1 by x. And integration of 1 by x will be log x, because differentiation and integration are opposite of each other, reverse of each other. So differentiation of 1 by v is log v. It's ln v in fact, because log means the base 10, ln means base e. So I'll write it as ln v, ln v, which means the base is e, with a lower limit and upper limit. And you know, you can write upper limit minus lower limit, so ln v2 minus ln v1. And you know, in logarithm, log a minus log b is ln v2 by v1. This is got base e, right? And to convert it to base 10, you have to multiply with 2.303 nRT log v2 by v1, where log means is base is 10, ln means base is e. Okay. Now you know PV is a constant. So P1 V1 is equal to P2 V2. So P1 by P2 is equal to V2 by V1. So instead of V2 by V1, I can also write P1 by P2. Work done is 2.303 nRT log P1 by P2. These are the two formulas that we use for isothermal process. I hope you're clear. Till this is what I taught you today. You have to be damn clear, damn thorough, so that tomorrow morning when I see you at 10, I can continue.